Hi everyone, in this video, I'll walk through our modeling approach for the RECS regression assignment, where the goal was to minimize mean absolute error or MAE while ensuring that the model was well fitted and generalized well to unseen data. Our notebook follows a progressive structure, starting with the baseline models and ending with a more advanced final ensemble model, which was the most important part of our approach. So we begin by importing standard libraries and loading the training and test datasets from Google Drive links. After loading, we inspect the dataset using head and info to verify column types and missing values. Next, we separate the ID columns for the features, define the feature matrix X and target Y, and prepare the taste data for submission prediction. And we then build a pre-processing pipeline using Sklern. And for this one, we actually use column transformer. Numerical variables are imputed using the median and scaled, while categorical variables are imputed using the most frequent value and one hot encoded. This ensures consistent pre-processing across training and prediction. For modeling progression, we start with a gradient boosting baseline, and this actually made training MAE that is close to 7.54 and validation MAE that is close to 9.32, which showed clear overfitting. We then tuned the model with a slower learning and reduced step, improving validation MAE slightly to about 9.22. Next, we introduce feature engineering and remove extreme outliers from the top 1% of the target distribution. With a stronger gradient boosting configuration optimized for MAE, validation MAE then improved significantly to close to 8.47. However, the most important part of our notebook is the final submission model, which uses CatBoost with an ensemble approach. For the final model, we first clean the special missing value codes like negative placeholders and replace them with NaN. Then we created additional engineered features such as square footage per person, rooms per person, logarithmic transformation, and interaction features to better capture household characteristics. We identified categorical columns explicitly and allowed CatBoost to handle them directly instead of one-hot encoding, which improved efficiency. We also trimmed the upper tail, and then the final approach used two CatBoost models with different parameter settings and random seeds. Each model used early stopping with overfitting detector to prevent excessive training. Finally, we clipped the extreme prediction based on training distribution and generated the submission file for Kaggle. And the final model has the best MAE of 7.98. So overall, while earlier models help guide improvement, the CatBoost ensemble with feature engineering, trimming, and early stopping was the key component to our final solution.
Next, we'll talk about how we improve the performance of our regressor through several stages, with each stage targeting a different source of prediction error. The first improvement was establishing a reliable pre-processing pipeline. By properly imputing missing numerical values using medians and handling categorical variables consistently, we reduce noise introduced by incomplete data. This ensures the model learns patterns from real signal rather than artifacts caused by missingness. The second improvement involved hyperparameter tuning of gradient boosting. Our baseline model produced a validation MAE of about 9.32, with training MAE around 7.54, indicating overfitting. To improve performance, we reduced the learning rate from 0.05 to 0.01, increased the number of trees, lowered the tree depth, and introduced subsampling. These adjustments improved validation MAE slightly to about 9.22, showing better generalization. The largest performance gain came from feature engineering. We created features such as square footage per person, room density, and people per bedroom. These variables capture household usage intensity, which is directly related to energy consumption. Adding domain-informed features allowed the model to capture nonlinear relationships that were not explicitly present in the raw data. We also addressed extreme values in the target variable. Because MAE penalizes large errors linearly, outliers can disproportionately affect optimization. By trimming the top 1% of the target distribution and optimizing the model directly for MAE using the absolute error loss function, validation MAE improved significantly to about 8.47. The most important performance improvement came from transitioning to CatBoost. CatBoost natively handles categorical variables and often achieves stronger performance on mixed-type tabular data compared to traditional gradient boosting. Using CatBoost reduced the need for extensive preprocessing and allowed the model to capture complex interactions more effectively. We trained two CatBoost models with slightly different parameter configurations and random seeds, then averaged their predictions. This ensemble approach reduces variance and typically improves predictive stability. Finally, we applied clipping to extreme predictions based on the training distribution to prevent unrealistic outputs that could increase MAE on the test set. As a result of all these improvements, our final validation MAE decreased to approximately 7.98 compared to 8.47 from the previous model, representing about a 6% improvement in error.
To assess and improve the fit of our regressor, we focus on measuring how well the model generalized to unseen data and actively controlling overfitting throughout development. The primary method we used to assess fit was comparing training MAE to and validations MAE. In the baseline model, training MAE was approximately 7.54, while validation MAE was 9.32, producing a differences of about 1.78. This gap indicates that the model was learning the training data too closely and not generalizing well. To improve the fit, we introduced several regularization strategy. We reduced model complexity by lowering tree depth and slowing the learning rate while increasing the number of estimator. This allowed the model to learn more gradually and reduce variance. After this adjustment, validation's MAE improved slightly to about 9.22, and the overfitting gap narrowed. We also incorporate subsampling in the boosting process, meaning each tree was trained on only portion of the data. This introduced randomness and helped prevent the model from relying too heavily on the specific observations, which improved generalizations. Another important step was removing extreme outliers from the target variable. Outliers can distort the optimization process and cause the model to fit rare cases too strongly. By trimming the upper tail of the distribution, the model focused on learning the dominant pattern in the data, which improves stability and reduced validation MAE to 8.47. When we transitioned to CatBoost, we used early stopping with an overfitting detector. During training, the algorithm continuously monitored validation's performance and automatically stop when improvement plateau. This prevents unnecessary complexity and is one of the most effective ways to ensure good model fit. Finally, ensembling two models improve fit further by reducing prediction variance when individual models make different small error. Every, averaging them often produce a more reliable final prediction. Overall, we assess and improve model fit through comparing training and validations MAE, applying regularizations and subsampling, trimming outliers, using early stopping, and leveraging ensemble methods. This strategy ensured that our final model achieved a validation MAE of about 7.98 while maintaining strong generalizations performance. Overall, our approach focused on managing the bias variance trade-off, where earlier model had high variance and later models achieved better balance through regularizations, trimming, and ensembling. Thank you for listening.